In question 1, we've got coffee sold in packets. We've got the frequency table here summarizing the information on a random sample of 90 packets. We've got a histogram drawn, and the 245, 248 class is represented by a rectangle having a width of 1.2 centimeters and a height of 10 centimeters. And we need to calculate the dimensions of the class spanning from 255 to 260. I will draw up a table with frequency, class width, and frequency density. For the 245 to 248, we know that the frequency is 15. The class width is the difference between the two class endpoints, so that's going to be 3. And the frequency density is found by dividing frequency by class width. So in this case, it's 15 divided by 3, which gives me 5. Now the 255 to 260 has a frequency of 9, as we can see on the frequency table. The class width is 5, so 9 divided by 5 gives me a frequency density of 1.8. Now to find the width, I'll be looking at the class width. So we know that 3 units are represented by 1.2 centimeters. So 5 units will be represented by x centimeters. So x is going to be 5 times 1.2 over 3, which gives an answer of 2. And for the height, we're looking at the frequency density. So a frequency density of 5 is represented by 10 centimeters. So 5 corresponds to 10 centimeters. So 1.8 corresponds to y centimeters. So to find y, I'll be multiplying 1.8 with 10 and then dividing by 5, which gives an answer of 3.6. And therefore we conclude that the width of this bar will be 2 centimeters and the height, it's going to be 3.6 centimeters. In part B, we need to use linear interpolation to estimate the median mass of the contents of a packet of coffee. Now we've got the frequency table here. We know that we've got a total of 90 packets. So to find the median, I'm going to do 90 over 2, which gives me 45. I will then go to my frequency table here and calculate the cumulative frequencies. So we start with 8. 8 plus 15 is 23. 23 plus 35 is 58. 58 plus 23 is 81. And 81 plus 9 is 90. So we know that the 45th observation would be in the 248 to 252 class. The next thing to do is draw a simple diagram here. We know that we are between 248 and 252. Somewhere along the way, we've got the median M. And in the below, I'm going to put the corresponding cumulative frequencies. We know we've got 23 observations up to 248. So 23 goes here. And 58 observations up to 252, and we're trying to interpolate for the 45th observation. So I'll be using ratio and proportion here. The small opening over the small opening is equal to the big opening over the big opening here, which means this takes me to m minus 248 over 45 minus 23 is equal to 252 minus 248 over 58 minus 23. We can proceed in solving for m. We've got m minus 248 over 22 is equal to 4 over 35. I can cross multiply to get m minus 248 is 22 times 4 over 35. And then I can add the 248, which gives me m to be 250.5, and the units are grams. In part C, we need to estimate the mean and the standard deviation of the mass of the contents. Well, we've been given this information here, the sum of the fy squared. I'm not going to use it. Instead, I will simply go on my class width calculator. I press menu and then option 6 and then option 1 variable, and I will actually reproduce the table on my calculator. For x, I'm putting the midpoint, so it's going to be 242.5, the first one, then it's 246.5, then it's 250, then we've got the 253.5, and then the 257.5, and then I'm gonna scroll to the right and go up and fill in the frequencies. So it's 8, then it's 15, then it's 35, then it's 23, and then it's 9. So I've inputted all the data on my calculator. I press option, and then it's option 3, one variable calculations. Well, the first entry, it's X bar. In our case, it's W bar. So the mean, which is 250.4, and it's measured in grams. And for the standard deviation, it's the sigma underscore X. So it's 3.95495, etc. Well, we've been asked to give our answer to 1 dp, so sigma W would be 4.0 grams. We're then told that the seller claims that the mean mass of the contents is more than the stated mass of 250 grams. We have been told that the actual standard deviation is 4 grams, and we need to test at the 5% level of significance whether this claim is justified. So we need to conduct the hypothesis test. My null hypothesis is that mu is 250, so the true mean is indeed the stated mean of 250 grams. My alternative is what the seller is claiming, which is that mu is greater than 250, and I'm setting my alpha level, my significance level, to be at 0.05. We know that sigma is 4, we've got 90 observations, so n is 90, and we have seen X bar, the mean, to be 250.4. Well, we know that if H naught is true, so under H naught, the sample mean follows a normal distribution with parameters mu to be 250 and sigma squared, the variance is the sigma squared over n, so 4 squared over 90. And we have actually seen 250.4. We inherit the direction from the alternative, so we need to find the probability of X bar being greater than 250.4. I will go on my calculator, I press menu, it's option 7, and then it's the normal CD, so option 2. My lower is 250.4. My upper should be something big and positive, so 10 to the 9. My sigma is the square root of 4 squared over 90, and my mu is 250. This gives an answer of 0.1714, so I'm just going to write this down. It's greater than 0.05, which means we have a non-significant result. We do not reject H naught, and this simply means that we have no evidence to support the seller's claim. Alternatively, we could have followed the critical region approach, which means we find the critical region and we assess whether we are in the critical region or not. So to find my critical value C, I need to solve probability of X bar greater than C to be 0.05, which means I can write this as probability of X bar less than C to be 0.95. Remember, I'll be using my calculator into the inverse normal mode to find the value of C, and therefore this should always be in the less than direction. So going on my calculator, I will press menu, option 7, it's option 3, inverse normal. My area is simply the probability of 0.95. The sigma and the mu are exactly what I had before, so no need to change the parameters here. And I get 250.69, so let me write this down. C is 250.69. This is the critical value, which means anything beyond this will be rejected. So my critical region is any value of X bar that exceeds the critical value, so X bar greater than 250.69. Well, we can see that the 250.4 that we have observed is not in the critical region, and therefore we have a non-significant result. We do not reject H naught, which again means that we cannot support the seller's claim. For E, we need to use our answers to parts B and C, so the calculation of the median and the calculation of the mean, to comment on the assumption that the mass of the contents will be normally distributed. Well, remember that we have found the median to be 250.5 grams and the mean to be 250.4 grams, so they are quite close. This is actually evidence in favor of the normality assumption, because we know that for a normal distribution, the mean and the median are exactly the same, because the normal distribution is a symmetric distribution. So all we need to say now is that since the median and the mean are close, then the normal assumption is indeed valid. In question 2, we've got a researcher believing that there's a linear relationship between daily mean temperature and daily total rainfall. So we've got the 7 places in the northern hemisphere from the large data set considered. We've got the daily mean temperatures and the daily total rainfall for the month of July in 2015, shown on the scatter diagram below. And with reference to the scatter diagram, we need to explain why a linear regression model may not be suitable for the relationship between T and S. Well, it would make sense to look for a linear model if we could see a straight line fitting on my scatter plot. Well, actually the points are not close to a straight line, and therefore we say a linear regression model may not be suitable. We then have that the calculated PMCC, the product moment correlation coefficient, turned out to be 0.658, and we need to assess at the 10% level of significance whether we have enough evidence for the population product moment correlation coefficient being greater than 0. I need to start by stating my hypothesis. My null hypothesis here is that rho is 0. Rho is the product moment correlation coefficient for the population, against the alternative which says that rho is positive. This is a one-tailed test because a direction is explicitly stated in the question. My alpha level in this case is set at the 10% mark. We have seen R to be 0.658 from 7 observations, so N is 7, and we need to find the critical values. I'll go to the tables of critical values for the product moment correlation coefficient provided in the formula booklet. I will go at a sample size of 7. I go to the left-hand side. At the 10% mark, I read off the critical value of 0.5509. So all we need to do here is state the critical value was found to be 0.5509, and therefore we need to compare what we have seen against the critical value. It is quite helpful to draw a bell-shaped curve centered at 0. We've seen a critical value of 0.5509, so anything beyond this is considered to be in the critical region and will therefore lead to a rejection of the null hypothesis. The 0.658 we've seen is actually greater than the 0.5509, so all I need to do is say 0.658 is greater than 0.5509. And therefore we say significant, reject H0, and we've got to interpret this in context. We've got evidence that the PMCC for the population is greater than 0. In part C, we need to use our knowledge of the large data set to suggest the names of the 2 places labeled G and H. So let's quickly look at our scatter plot. We've got the 7 locations. On the vertical axis, it's the rainfall, and on the horizontal is the temperature. Remember, all of the locations included here are within the northern hemisphere. If we take a look at the maps, seeing the locations, then obviously it cannot be Perth because Perth is in the southern hemisphere. Looking at the scatter plot, we see quite high temperatures around the 27 degree mark. So this will lead me to exclude any of the UK locations. So all of these are rejected. So I'm pretty much left with Jacksonville and Beijing. So my best guess will be Jacksonville and Beijing. In part D, we need to use our knowledge of the large data set, and with reference to the locations of the 2 places labeled G and H, give a reason why these places have the highest temperatures in July. Well, remember that the UK is over here. The closer I am on the equator, the higher the temperatures. So we can see that Jacksonville and Beijing are further south than the UK locations. They are closer to the equator, and therefore we conclude that they exhibit the highest temperatures in July. In E, we need to suggest how we could make better use of the large dataset to investigate the relationship between daily mean temperature and daily total rainfall. Well, in these kind of questions, the first thing you think is how you can increase the sample size. So maybe you could say collect data between May and October, not July only. Remember, the large dataset covers from May to October. It does not cover a full calendar year. Alternatively, as the mark scheme suggests, you could use data from one place and just concentrate on that place. In question 3, we've got a particular type of bulb with 36% growing into plants with blue flowers, the remaining growing into plants with white flowers, and we are told that bulbs are sold in mixed bags of 40, and Rasses is selecting a random sample of 5 bags. We need to find the probability that fewer than 2 of the bags will contain more bulbs that grow into blue flowers than those that grow into plants with white flowers. So we've got a nested binomial distribution here. I will start by focusing on the number of bulbs within a bag that grow into plants with blue flowers. So let me define my first random variable x to be essentially the number of blue flowers. We know that each bulb will either grow into blue or a white flower, so x follows a binomial distribution. The parameter n is 40 because I've got 40 bulbs, and the probability of success is 0.36. Now, the probability that we've got more blue flowers than white flowers is the probability of x being greater than 20, so more than half of the plants grow into blue flowers. So this is 1 minus the probability of x less than or equal to 20. So I'll go on my calculator, I press menu, it's option 7, and I go down and I go for binomial CD. It's option 2 variable. My x is 20, my n is 40, and my p is 0.36. This will give me the probability of x less than or equal to 20. So it's 1 minus 0.975996 ... So I go to menu option 1. So if I do 1 minus the answer, I get 0.02400. So let me write this down. And I will actually store this on A because I'll be using this later. So I press STO and A. It's been stored on A, so I'm maintaining full accuracy. And we now need to consider that we've got a random sample of 5 bags. So we're now wondering how many of these bags will actually turn out to contain more bulbs that turn into blue flowers than white flowers. So we need a new random variable. I'll call it y. Where y is the number of bags with more blue flowers. So in this case, y is binomial with parameter n being 5, and the probability of success is simply a, the probability we got just a while ago. And we want the probability of y being less than 2, which is simply the probability of y less than or equal to 1. So once more, I'm going to go on my calculator. I press menu, option 7. I go down to binomial CD, and I choose variable. My x is 1, my n is 5, and my p is simply a. So I'm just calling alpha a. And this gives an answer of 0.9945. I'm quoting probabilities to 40 p's here, even though 3SF would be acceptable in this case. We then have that Maggie takes a random sample of n bulbs. They are using a normal approximation, arriving at the probability of more than 244 of these n bulbs growing into blue flowers being 0.0521 to 4 decimal places. And we need to find the value of n. So let's start by saying that our random variable x is now binomial with an unknown parameter n and a probability of success being 0.36. Well, we know that if we are planning on using a normal approximation, then we need to find the mean and the variance of the binomial distribution, because this will be the mean and the variance of the approximating normal distribution. So the mean mu is found by doing np, which is going to be 0.36n, whereas the variance sigma square will be np times 1 minus p, which is going to be n times 0.36 times 1 minus 0.36, and this gives an answer of 0.2304n. So we know that x will be approximated by a random variable, say t, which follows a normal distribution with mean 0.36n and variance sigma squared 0.2304n. Now, we have been looking at the probability of more than 244. So the probability of x being greater than 244 is the same as the probability of x greater than or equal to 245. And the reason I'm doing this step here is for me to see the continuity correction that needs to be applied, because I'm approximating a binomial distribution which is discrete by a continuous distribution, the normal distribution. Now we know that the binomial distribution can only attain integer values, whereas the normal distribution can attain any value. So because I've written this as a strict and then as a relaxed inequality, the continuity correction is simply the midpoint of the two. So this will be approximated by the probability of t greater than 244.5. And I can now standardize, leading to the probability of z greater than 244.5 minus the mean of 0.36n divided by the standard deviation, which is the square root of 0.2304n. So this is the standardization, and I've been told that this probability was 0.0521. So I can actually proceed and say the probability of z less than 244.5 minus 0.36n over the square root of 0.2304n is simply going to be given by 1 minus 0.0521. So I can now use my calculator. So I go menu, 7, I go inverse normal, option 3, and I say that my area is 1 minus the 0.0521, and I keep the sigma to be 1 and the mu to be 0 because I'm in the standard normal distribution. See, the value I got is 1.6248, and I will actually store this on A because I'll be using it later. So this means that 244.5 minus the 0.36n over the square root of 0.2304n is equal to 1.6248 ... which we have stored on A. So I can now proceed into cross multiplying, saying that 244.5 minus 0.36n is equal to A times 0.2304n square root. Now, if I take the square root of 0.2304, it gives me a nice value, 0.48. So I've got 244.5 minus 0.36n is 0.488 times root n. And this is actually a disguised quadratic in root n. I will collect everything on the right hand side, leading to 0 is 0.36n plus 0.48a root n minus 244.5. I will say let w be root n, which leads to 0 being 0.36 w squared plus 0.48a w minus 244.5. And then I can simply use the calculator. I press menu. It's option A to solve a polynomial of degree 2. My coefficient for x squared for the quadratic term is 0.36. The coefficient of the x term, the w term in this case, is 0.48a. So I just write it like that, and I maintain full accuracy throughout. And then I've got the constant term minus 244.5. So we get one solution for w to be 25.000 ... and the other is minus 27.166. So that's the second solution. So or w is minus 27.166 ... remember that the W is simply the root of n, so I can simply write here root n is 25.000 or root n is minus 27.166. Well, root of n can never be negative, so I'll have to reject the right hand side, so I say reject, not valid, and therefore to find n, I will simply square the 25.000, which gives me 625 for n. In question 4, we've got a Venn diagram showing the probabilities of a student's lunch boxes containing a drink, sandwiches, and a chocolate bar, and we are asked to write down the probability of S intersection D dash, which means we need to be in S but outside of D. Notice that S is actually a subset of D, which means that it lives entirely within D, so it is never possible for me to be in S and at the same time outside of D. So the answer is simply that the probability S intersection D dash is 0. We then have 80 students bringing their lunchbox, and we know it is given that all 80 lunchboxes contain sandwiches and a drink, and we need to estimate how many of these 80 lunchboxes will actually contain a chocolate bar. This is an example of conditional probability. We know for sure that we contain sandwiches and a drink, so we know for sure that we are within the shaded part here, and we need to find the number of lunchboxes that will contain a chocolate bar. So I'm wondering what's the probability I'm here. So in other words, this is the probability I'm in C, given that I'm in S intersection D. So what's the probability that I contain a chocolate bar, given that we've got a sandwich and a drink? So this is what I have ticked, the 0.27, over what I have shaded, which is the 0.33 plus the 0.27, which gives an answer of 9/20. That's the probability. We need to turn this into an expected frequency, so I will be simply multiplying the calculated probability of 9/20 times the 80, which is the total number of lunch boxes, giving an answer of 36 lunch boxes as my answer to part B. We then have that the events S and C are independent, and additionally the probability of D given C is 14/15, and we need to use this information to determine the values of U, V, and W. Well, we know that if two events are independent, then the probability of their intersection is simply the product of their individual probabilities. So we can see that the probability of S intersection C is the 0.27, and we've got 0.27 is equal to the probability of S, which is 0.33 plus 0.27 times the probability of C, which is 0.27 plus V plus U. This leads to 0.27 is equal to 0.6 times 0.27 plus V plus U. And if I divide both sides by 0.6, I get 0.45 is equal to 0.27 plus V plus U, which of course gives me 0.18 is equal to V plus U. So I have established a relationship between V and U. They add up to 0.18. It's time now to look at the second piece of information. It says probability of D given C is 14/15. Conditional probability, I know for sure that I am in C. So if I'm in C, I'm here, here, or here. The probability I'm in D is simply these two. So I can now say that the probability of D given C is what I have double ticked, the 0.27 and the V, over what I have ticked once, so 0.27 plus V over the 0.27 plus V plus U, and this has been given to be 14/15. Now notice that the denominator is exactly what I had here, the 0.45, which means I can now write that 0.27 plus V over 0.45 is equal to 14/15. and I can cross multiply to get 0.27 plus V is equal to 0.42, which leads to V being 0.15. Now if V is 0.15, then I can go here and find the value of U. So we have 0.18 is equal to V, which is 0.15 plus U, and therefore we know that U must be 0.03. And finally, if I add the probabilities here, I should be finding a result of 1. So if I add everything, this means that I've got W plus 0.33 plus 0.27 plus V plus U is equal to 1, which means I've got W plus 0.33, where the 0.27 plus V plus U is 0.45, so plus 0.45 is equal to 1, which leads to W being 0.22. In question 5, the lifetimes of batteries sold by company X are normally distributed with parameter mu 150 and standard deviation sigma being 25 hours. We need to determine the expected number of batteries that have a lifetime of more than 160 hours. We're looking at a box containing 12 such batteries. Well, I will start by defining X to be my random variable corresponding to the lifetime in hours. It follows a normal distribution with mu 150 and sigma 25. I want to find the probability of X being greater than 160, so I will simply go on my calculator, menu 7, normal CD, my lower is 160, my upper is something big and positive, so I'm going to put 10 to the 9, my sigma is 25, and my mu is 150. This gives an answer of 0.344578. So let me write this down, 0.344578 ... This is not my final answer, so I'm just going to store it on A to proceed. Remember, we've got 12 batteries within a box. So I will define the random variable T to be the number of batteries lasting more than 160 hours. And we're wondering how many of these batteries will actually turn out to be lasting for more than 160 hours. So this is obviously a binomial distribution with parameter n being equal to 12 and probability of success being simply A. The expectation of T, the average, the expected number of batteries is given by NP, which is 12 times A. So I go on my calculator, menu 1, I do 12 and simply A. And this should give me the answer, which is 4.13. So I'm going to keep the decimals, it's okay because it's unexpected, it's a theoretical mean, so 4.13 batteries is the answer to part A. We are then told about the second company Y, also selling batteries. Their lifetime is normally distributed with mean 160, and 80% of these batteries turn out to have a lifetime of less than 180 hours, and we need to find the standard deviation. So let me start by saying that Y here follows normal with mean 160 and unknown standard deviation sigma. We have been told that the probability of Y being less than 180 is 0.8, and because I've got one of the parameters unknown, I'm going to standardize. So this is the probability of Z less than 180 minus 160 over sigma being equal to 0.8. I'm going to go to my calculator once more. Menu 7, I'm going to go for inverse normal. My area is 0.8. My sigma is 1 and my mu is 0 because I'm in the standard normal distribution. I get an answer of 0.8416, which means that the 180 minus the 160, so 20 over sigma is equal to 0.8416 ... I can store this on B on my calculator. So let me put a B here, which means we've got 20 is equal to B times sigma. So 20 over B will give me the value of sigma. So menu 1, I do 20 over B, and I get an answer of 23.8 hours. So sigma is 23.8, and the units are hours. We are then told that both companies sell their batteries for the same price, and we need to state which company we would recommend, giving reasons for our answer. Well, if we go back, we can see that X is lasting for average of 150 hours, whereas Y is lasting for an average of 160 hours. So the first thing we could say is that there's a higher mean for company Y, so this means that the batteries last on average longer. And we can also look at the standard deviation for the X company. We've got a standard deviation of 25 hours, whereas for company Y, we've got 23.8 hours, so a bit less. So we could also say that there's a lower standard deviation for Y, which means we have more consistent lifetimes. So both of these lead to us recommending company Y.